So yesterday we were discussing about this structural magic number. So the magic number means the number of atoms in a cluster, which gives rise to a stable cluster. Okay, so if you have like certain number of atoms in a cluster, so those clusters will be more stable compared to other clusters. And the principle is based on that you have to maximize the density, so minimum volume and maximum density, and then also you have to minimize the surface energy. And what we saw, that if you take a FCC lattice, so arrangement of atoms in FCC structure, so you can have certain number of atoms or magic numbers which will give rise to these stable clusters. So like you can have 13 atoms, 55 atoms, 147 atoms, and so on. So which will keep the structure like FCC like structure, and they will be stable. Okay, so this does not mean that you cannot have clusters of any other uh, sizes. So it may not, it doesn't mean that you cannot have clusters with maybe 15 atoms, or let's say 20 atoms in this case, or 25 atoms. It is possible, but the clusters with this number of atoms, if they are forming a FCC like lattice, so these uh, the clusters with this number of atoms will be stable. So we also saw that the size or the shape actually depends on the number of atoms you have. So you can also have a transition from like FCC like to HCP or icosahedral. So you can also have a phase transition in a cluster. The structure can change from one configuration to another. So here are some examples of the clusters we like that exist in experiments. People have observed this kind of clusters. So you can see like you can have carbon 20, sodium, magnesium, so like with 20 atoms, but they have again different shapes, or the geometry is different, right? uh, and so since the structure is different, or the geometry is different, so it depends on what kind of atoms that are involved in creating that cluster. But in all these discussions, we only look at the structural part or the geometrical arrangement of the atoms, but we have completely ignored the electronic structure. Okay, so the electronic structure is completely ignored, but that actually we have to consider that, because how we feel electrons in these energy levels, so that can play an important role in determining the actual cluster size and the shape. So why it is that? So before that, just a brief some discussion about this synthesis of clusters. So how one normally synthesizes? So there are many different ways, but one of the first methods how the clusters were synthesized is basically you take like your metal which you want to uh, from which you want to create your clusters. Okay, so this is your metal disc here, you put here, right? And then you shine it with a laser beam. so high power laser beam, so that you get an ablation of these metal nanoparticles. And then you have also like a flow of helium gas here, and then with this gas flow, so you can take, so you have this ablation of material due to exposure to laser light. And then you have various kinds of clusters, so depending on the material you have taken, so you can have different clusters. Let's say this is so clusters with different sizes. So this N stands for the number of atoms in the metal cluster. So you can have a different number of different sizes, clusters with different sizes. So this is, you get like a beam, and then you pass it through a like like uh, schemer, okay, and then you look at there, or you do a mass spectrometry to know the cluster size, or how many atoms you have in the cluster. Okay, so this question is like the mass spectrometry. What is mass spectrometry? So that you guys read a little bit, and then you tell me. So we'll discuss, or you tell me tomorrow, that what is mass spectrometry. But what you get this from the mass spectrometer? So typically, these are the results experiment what you get. So you get number of counts for each cluster. So how many clusters you have. So like you have, like if you have a photon detector, so you count number of photons, or you count number of X-rays. So similarly here you can count the number of clusters you have in the beam. And then in the x-axis what you have is number of atoms in a cluster. So you can also calculate the number of the cluster size basically. So what was observed here, so this was done for a lead metal, so the clusters were of lead. And if you perform that experiment, what was observed is, so number of counts were larger for 7 and 10. Okay, so you get clusters, so more number of clusters have 7 atoms or 10 atoms. Okay, so this is like from the experiment that was observed. Although if you, so lead is actually a FCC lattice. Okay, so this is FCC. So if it follows the structural magic number, what you expect is you should have clusters of stable clusters, or more number of clusters should be of this dimension, either 13 or 55 and so on. So not 7 and 10. Okay, so that was surprising. Okay, and to understand this, one has to actually understand the electronic structure. So it is not really the geometric structure or the arrangement of atoms in different crystal form that decides which cluster will be stable. Rather, it is the number of electrons which actually are going to decide, or the electrons energy levels, which is going to decide which cluster size will be stable, or you will get more number of clusters of that size. So it is very similar to this atomic like electronic structure in atoms. Okay, so the top one is like a ionization potential. So this is on the y-axis, what is plotted is ionization potential, and on the x-axis is the atomic number. Okay, so I'll just zoom it in. Okay, so this is your atomic number versus ionization potential. So what you observe here is like the ionization potential is maximum. So that means difficult to ionize are with electrons with 2 and 10 and 18. So this represents your helium, right? So this is your argon, sorry, neon. This is your argon. So this is what, when you look at the ionization potential as a function of atomic number, that is what is you observe. So this is kind of a magic number. Okay, so this is your magic number for atomic electrons. So you get a fully filled electrons. So the cell is completely full when you have two electrons or 10, 18, 36, and so on. So this is exactly what happens in case of clusters as well. So this is an experiment again of ionization potential, okay, of a cluster. I think this was a sodium cluster probably. And what you observe is like ionization potential peaks. So some peaks appear for 2 and then 8 and so on. So we'll see some other experiments also which describe this similar this measurement of ionization potential. So here the magic numbers are like you have 2, 8, and then the next one is 20. Oh yeah, it is written here. So what you have is your magic numbers are, this is your magic number in case of sodium clusters. So this is observed in experiments. So that means the clusters with these many atoms are much more stable, or there is probability to find these clusters in more numbers compared to other cluster sizes. Okay, so this is quite surprising, but it actually happens and observed in experiments. So again, this plot here shows the same thing what I described before. Okay, so there are different experiments done by different people, different groups. So again, here is a measure of ionization potential as a function of, yeah, here you, this is nuclear charge they have plotted. So atomic number basically. So you increase, as you increase the atomic number, so what you see is the ionization potential is higher for uh, this helium, neon, and argon, these gases. So that means if the electronic cell is completely full, so you get, so this is kind of the magic number what you have for electronic structure. And then exactly the same thing again is done here with sodium clusters, and you see these magic numbers like 8, 2, 8, 18, 20, 40, right? So these are the numbers you see here, which gives rise to the maximum ionization potential. So that means they are much more stable compared to other clusters. Yeah, this experimental plot again shows the same thing. This is done by some other group, and you again see the same magic numbers which come out actually when you look at the cluster size, the number of uh, or the counting rate or the number of clusters which will have this cluster size. So how do we understand or why this happens? Okay, so this is a very interesting thing happens here. So, and to understand it, we have to go to modeling of this cluster
Hello, sir.
size. Yes,
Sir, what is this counting rate?
counting rate is number of clusters. So if I say I have, let's say, so if it is depending on the number, of course there is no, let's say, how do you say, no, nothing, no number is mentioned here. So typically it's like I have 10. So if I am doing a experiment and I have, let's say, 100 clusters, so out of that, so maybe 5 will be with size with atoms, like 4 number of atoms. So maybe 10 clusters which will have 20 number of atoms, and another maybe 12 number of clusters which has, let's say, 30 number of atoms. Okay, so this is the count. So number of clusters that your detector detects, basically. Okay, so this counting rate is high means if the cluster size or the cluster has 20 atoms, so I have a higher number of that cluster. So similarly, this peak here represents that a cluster with 8 number of atoms has I mean observed more compared to other cluster sizes. Okay, so similarly here 40, 58, and so on. So this is like how many times you observe. So counts will be like number of. So in X-rays, if you have done X-rays, for example, so you count the number of photons or number of X-rays per second. Okay, so that is your counting rate. So how many photons are striking your detector per second? Okay.
Okay, sir.
So the question is, how do we model it? Based on electronic structure. So we again go back to the atomic scale. So like if you take a hydrogen atom, for example, so basically what you have to do is you solve the Schrodinger equation, which is written here. So you have the kinetic energy term, potential energy term, and you calculate. So you have the Hamiltonian, and then you know the energy eigenvalues of the electrons in a hydrogen atom. So the picture is very similar, like you have a proton, and then you have an electron which is revolving around it, and then you have the potential, which is an attractive potential between your electron and the proton, and then you solve the Schrodinger equation, and you get, so your wave function, it basically will have a radial component and then angular component. Okay, so it's a function of r, theta, and phi. So then you can also fill it up this electronic, so you get this discrete energy levels. Okay, so this all you know already. So you have n equal to 1, l equal to 0, and ml again. So for different energy levels, so you have a different number of electrons. Okay, so you can go on filling up electrons in different cells. So n equal to 1, 2, 3, and so on, and then you get this magic number. So like if I have n equal to 1, will correspond to your 1s orbital, right? So you have two electrons, then you have 2s and 2p. So you have here 8 electrons, and total will be 10. Okay, so this is your magic number. Then you have 3s, 3p, and uh, so again the energy which is lower energy, so that will decide which will be your uh, the next field orbital. Okay, so on. So you can have here so 3s2, so again 8. Okay, so 3d will be a higher energy. So you have the magic number is 18, which is your argon, and then you fill it up this 3d level and 4s and so on, and then you go to uh, your krypton, so 36, and so on. Okay, so this is how this magic number in electronic structure works. So you have 2, 10, 18, and 36, and so on. So we can now, let's say, go to a next higher level. So let's say we have two electrons with one nucleus. So basically it's like hydrogen the molecular ion. Okay, H2 plus ion. So you have one nucleus, a proton, and then you have two electrons which are attached to it, and the potential now looks a bit different. Okay, so you have a attractive potential between this electron A and your proton. Then also you have attraction between electron the second electron or B electron, and so this might be at a different distance. And then you can also have a repulsive potential here. Okay, so this electron-electron repulsion can also happen. So the potential will be different now. So you can again solve the Schrodinger equation, and then you basically you get these molecular orbitals. Okay, so you get the molecular orbitals in this case, and then you fill it up accordingly. So the point here is like if we increase from one electron and one proton, we go to two electrons. Now the complexity increases, and it is now becomes difficult to solve quantum mechanically. And even now, if I'm talking about clusters, so where I have more number of atoms, so that means more number of electrons and nuclei, and the interactions will be interaction terms or the potential will be very complex or very complicated, and it is not easy to solve the Schrodinger equation in that case. So one needs lots of approximations to solve it. Okay. So basically, so you can take a similar approach to solve the electronic structure of clusters. Okay. So let's say we take an example of sodium cluster here. So sodium atom has 11 electrons and 11 nuclei. So the potential, this potential term V R will be complicated because you have electrons interacting with electrons with 11 protons, then electron with electron interaction. So there are lots of interaction terms that exist here in this potential. Okay, so when you describe the interaction terms, and so typically, so you like many of you have already heard that this is like a many body problem in quantum mechanics, and to solve that you use like perturbation and approximation, various approximations. So one way, like easy way is, or simpler way is, like you take, let's say if you take a single sodium atom, so we can describe it as a sodium ion, okay, and with one electron or a valence electron. So this ion we define as we have 11 nuclei plus 10 electrons. So 10 electrons basically, so this Na plus is like a completely filled electronic cell. So therefore we take this as a background or Na plus, where one single electron is interacting with all this Na plus ion. Okay, so this is a simpler because when we are, why we use this approximation, because most of the properties of this material, so sodium for example, will depend on this valence electron. So the single electron will decide the its electrical properties, its chemical properties, uh, and so on. And therefore, this is a good approximation to start with. And so we can say this valence electron is basically it's like a free electron which is interacting with this all this in a potential of the sodium plus ion. So if we go to this cluster, so now we have n number of atoms. Okay, so instead of so capital N. Okay, so this is the number of, so we have n number of nuclei, and or sorry, we have yeah n nuclei, and then we have 11 into n electrons. So 11 electrons from each, and here we have also 11 protons. So 11n nuclei and 11n electrons. So basically we have like, so this here you can, so this is like you can consider like a background, like a positive background you have. So if you are writing the Schrodinger equation, in that case you need like 12n. So basically you have 12n particles. So n here represents your number of atoms. So this is a very complex problem. So like we did for atom, so we can similarly do a approximation here. So what we can say is, so we have n nuclei plus 10 into n electrons. So that we say we have, let's say, n number of sodium plus ions, and then these there are n valence electrons, so each will be giving one valence electron. So since we have n number of atoms, so we have n valence electrons, and total will be 2n particles we have. So now the problem has is reduced or becomes simpler, but it is not still easy to solve analytically or numerically. And so there is one approximation which is quite well known in the cluster physics. So this is known as this Gilliam model. Okay, so it is actually based on this approximation what we did here. Okay, so where we assume that we have n electrons, these valence electrons, which are interacting with this n number of sodium plus ions. And the basic assumption is like these n electrons are experiencing a mean field, or like a field which is an average field due to all these ions. Okay, so which forms like a gelium like structure. And then these electrons, these valence electrons, are almost so exactly the same thing. So they are seeing a average ionic structure, and then use so different like density functional theory, or the different or molecular dynamics to calculate the energy levels. So this is normally is done numerically, so you can calculate the energy levels. And here this picture actually presents that. So on the left side, what you see is like you have the cluster. Okay, uh, so when you solve the or using this approximation, so what you get is, so on the left side you have the electronic energy levels, on the right side you are electronic energy level for the cluster. So this is electronic energy level for the atoms, and this is electronic energy levels for the cluster. So you clearly see there is actually a difference here. Okay, so you have, so in case of electrons you have this 1s, 2s, 2p, but here in case of electrons in a cluster, so you can have 1s, you can have 1p, 1d. So this is a different quantum numbers you have. Okay, so different electronic level you get. And this Galium model is yeah, briefly or like a schematic I presented here. So it's like you have a potential well of this positive ions, and your free electrons or these valence electrons are basically confined in this potential well. So you can solve it using different like this quantum mechanical models. So if we say we have this potential well, it's like a 3D potential well, and and so you can have different potential well models, right? So this is like you can have a spherical, like a harmonic oscillator, like uh, potential well, or you can like distort it a little bit, and you can have unharmonic this spherical unharmonic well. You can also approximate like a box, very similar to like electron in a 3D box. So you can say it's in a potential well, square well. So these are approximations one can take and you can solve, and then you basically get these magic numbers which will give rise to a filled electronic cell for the cluster. So if you do that, this approximation, so you have 2, 8, 20, 40, 58, 70, 92, and so on. So different potential approximated potential will give rise to slightly different magic numbers, but they actually more or less matched with this experimental observation. So that's why these models or these approximations are quite uh, relevant. So you can use this kind of approximations. Okay, so here just mention this different potentials. Yeah, here this again this picture here shows the same. If you take a harmonic oscillator, simple harmonic oscillator like potential, and then this is how the energy levels will be. So you have 1s, 1p, 1d. So you have all different levels uh, that are possible for this harmonic oscillator, and then you get this magic numbers 2, and then so 2, 8, 20, 40, and 70, and so on. And this is what again like these experiments what we saw before, that tells you. And again this another group another experiment where they again observed these magic numbers. Okay, so again this intensity or this counts what they are counting, and the cluster size, and again you see this magic numbers. So here what you see is this number 70 is actually missing. So we said 70 should be present, but 70 is missing. So it depends again on the size of the cluster. Okay, or the rather than the size, actually how if the cluster is like deformed or not. So if the cluster gets a little bit deformed, so it can happen that some cluster size can be missing as well. Okay, uh, so these are like Okay, so can you hear me now?
Yes,
Yes,
sir.
sir.
Yeah, okay, sorry. So there's, let's share the screen again. Yeah, so I was telling that in sometimes there is a little bit deviation from the model, exact model, and it could happen due to some distortion or deformation in the cluster, so which could lead to some magic numbers that may not exist in when you calculate the electronic structure. So what these numbers now represent, that if I take clusters with 8 number of atoms or 20 number of atoms or 40 numbers of atoms, so I have like a filled electronic cell. So the outer cell of that label electronic label of the cluster is completely full. So like similar to, you have, if you take helium, neon, argon, and so on. So this is known as electronic magic number. So what we observed is like two different magic numbers, right? So one is the structural one, and the other is electronic one. So one is driven by or dominated by the arrangement or the geometry of the atoms, how they are arranged. So that leads to a magic number or clusters with 13 number of atoms stable or 55 number of atoms stable. Okay, but if I look at the electronic magic number, so that means if we say we have clusters where electronic levels of the electronic cells are completely full. So in that case, which clusters are stable? The configurations with 2 number of atoms or 8 number of atoms or 20 and so on. So this is like a confusion you might have, right? So the question is, which magic number decides like which cluster will be stable, right? So whether this cluster or the cluster size, will it be dominated by the structural magic number, or will it be dominated by electronic magic number? So the answer is, so if we do experiment, so that suggests that if you take small clusters, so for small clusters, normally this electronic magic number dominates. So for small clusters, this electronic magic number which decides, basically tells you which cluster size will be stable. But if you go to a larger cluster, then the structural magic number will decide which cluster sizes will be stable. So that means if you take large number of atoms, so the electronic structure doesn't matter, and you can think why, because now you don't have this electronic levels, discrete energy levels anymore, rather you have these bands. So therefore the how these atoms or the size of the atoms or the cluster will be decided by this geometric arrangement. Okay, so they would like to arrange in such a way that the geometrical factor is becomes more important. But if you have a small cluster size, so you have more discrete energy levels, and how you fill the electrons in these discrete levels, so that decides uh, your cluster size. Okay, so therefore the electronic magic number normally dominates for small cluster, and this typical transition happens around this value of n equal to 8. I mean, this is not a like a clear, like what we were discussing yesterday, no, how many like atoms you will have to have a transition from cluster or nanoparticle to a bulk like behavior. So this again is not really like a, so similarly like yesterday I said, so this depends on what properties we are looking at. Okay, So if you are looking at the melting point, so the transition from a nanocluster or nanoparticle to the bulk will happen with for different number of atoms. So if we are talking about the electrical conductivity, that can this transition from nano to bulk can happen for different number of atoms. Okay. So similarly, this also can be different. So depends on also that also depends on which atoms we are talking about. Okay, but more or less, if you have like typically FCC kind of like if we are talking about the structural unit as a FCC, so typically if you have this 12, 20 atoms, so n equal to 7 up to n equal to 7 cells, so it is decided by the electronic magic number. And if you go more than n equal to 8, so you have like more number like 1500 or more than 1000 or let's say 1400, 15 atoms. So the arrangement or the size will be decided by the structural magic number. So that means the closed cell electronic configuration is like more stable at small cluster size, and you can imagine that it is very similar to something like what is known as super atoms. Okay, so you can call them as super atoms because it's very similar to like atoms and how the electronic. So you fill the electrons in the to complete the electronic levels. So you can call these clusters as also super atoms. Sometimes in literature you will also find that term. Okay, so these are the two things which we discussed about last so yesterday and today. So these magic numbers which decides how you can create a stable cluster or you can get a stable configuration. So depending on the electronic structure, or it can be decided by the geometrical structure. Okay. So this is for today, and then tomorrow we will continue with some of the like extend these ideas to different applications a little bit. So we'll look at different clusters, so metallic clusters, semiconducting clusters, and magnetic clusters, and so on. Okay, any question?
So,
Yes.
can we say here that stability is directly dependent, or stability is magic number is the only factor to determine the stability of that cluster?
Uh, Look, as I said, uh, magic number doesn't mean that all clusters will have the same number of atoms. Like you cannot have clusters with different number of atoms. So if I take sodium atom for example, okay, a sodium cluster. Okay, so magic number is like let's say I said 2, 8, uh, 20 and so on. Okay, so that doesn't mean I cannot have a cluster with 12 atoms. I cannot have a cluster with 13 atoms or 15 atoms. I can have, but they will be much more reactive or unstable. Okay, so that means if you can stabilize them in some way, so yes, you can have those clusters with those number of atoms. And there are, so this study of clusters with different sizes. So let's say for example you can type in Google like what is the stable configuration for a gold cluster. Okay, and you will observe like you'll see plenty of papers on that, theoretical, experimental, and people are still, it is like clearly it's a debate still going on, a research going on, that uh, which cluster size will have what kind of structure. So now if I take a cluster with 20 number of atoms, so I'll have certain kind of shape. Okay, so geometric arrangement. But that can also change if I take let's say 22 number of atoms. So it may not be as stable as a cluster with 20 atoms, but it is still possible. Okay, and it can be, but you might need a for certain applications. So there was some example like on Monday, someone was saying about catalysis for example. So if you want to use it or for some chemical reactions you want to use, So you want to see how reactive it is. So in that case, you do not want a cluster with 20 atoms. So you say, I want a cluster with 22 atoms or 23 atoms or maybe 18 atoms. So that is much more reactive. So if you are doing a reaction to a gas, okay. So therefore, this magic number is like gives a framework that okay, these clusters with this number of atoms will be much more stable compared to other clusters. That's all. It is not nothing to do with like you cannot have other clusters, other sizes of clusters. Okay.
Yeah, it means matlab, what I understood that we can have cluster, but for that stable cluster, we should have that kind of magic number for every kind of atoms, right?
Yes, this magic number is uh, for all like a cluster. If you have these magic numbers, so you have a stable cluster. That is all. This point here is.
Okay.
I mean, maybe I missed what is exactly your question.
So my question was is that magic number is the only criteria to determine the stability of that cluster or that particular atom?
Yes, yes. Right. Yes. Yeah, yeah, yeah. So the magic number is, I mean, magic number. Why it is called magic number? Because this is like a number which gives us like a stable cluster. Okay. So it is not magic number which is deciding this stable cluster. Rather, what is, as I said, the electronic structure or the geometric structure that is deciding which cluster will be stable. Okay, so it is not a number that is deciding. So this number is a consequence of the electronic structure or the potential well. So this potential well, like how the potential well is, so that decides okay, a cluster with 20 atoms will be, or with 8 atoms will be completely full. Okay, so it is not like the number is a consequence. Okay, just to give you a flavor. But what is the underlying physics is, it is either the structural arrangement of atoms, how the atoms are arranged, or how the electronic level will be due to this ions. Okay, so that decides which configuration will be stable, and these numbers are kind of a outcome of that.